So one thing that we can tell from seismic waves is how far from our recording from our seismograph that the actual earthquake event occurred. And the way that we do this is we look at our seismogram and we see when the arrival of the P wave was, and then when the arrival of the first S wave was. And we look at the difference in time between these two. So in this example here, each one of these vertical lines is 1 minute. So that would be 1, 2, 3, 4, 5 minutes between the arrival of the first P wave and the first S wave. So the S wave is slower, and the further away you are, the longer it's going to take for the S wave to get to you. This is really similar if you've ever done this. If you ever see a lightning strike, or lightning in the sky, if you want to know how far away the lightning is, you can count the number of seconds until you hear the sound of the thunder, and that will tell you how far away the lightning strike is. The reason for that is because the light waves travel much faster than the sound waves. So the light waves are almost instantaneous, and then we have to wait for the slower sound waves to get there. So for example, if a lightning strike occurred 1 mile from where you were standing, then it would take 5 seconds between when you see the lightning and when you hear the thunder. But if you were 3 miles away, it would be a full 15 seconds between when you see the lightning and when you hear the thunder. The same is true with S and P waves. Now we've kind of turned the seismogram on its side, but here is zero time, and then we're going up in time here. The P wave occurs, and then the S wave occurs 5 minutes later, just like we saw on the last seismogram. If we were right at where the earthquake occurred, if we were standing right there as the earth was shaking beneath our feet, we would essentially feel the P wave energy and the S wave energy at the same time. But as we get further away, and this is pretty far, right? 1,000 kilometers would be 600 miles, 600 miles, 1,200 miles, 1,800 miles, maybe about 2,300 miles here. We would have 5 minutes between when we feel the shaking from the P wave and when we feel the shaking from the S wave. That may have died out a lot, so it's not much shaking. We might need a seismograph in order to record that, but there would be this time lapse because the P waves are faster than the S waves. And because of that, if we just have a seismograph, we can just slide that seismograph up and down until the area between the first arrival of the P and the first arrival of the S fits between these two curves, and then we can see how far away our seismograph would be from where the earthquake occurred. And this is what we do. So in order to locate an earthquake, what we would do is we would take measurements of the earthquake from at least 3 different places, in this case Paris, France, Montreal, Canada, and Sao Paulo, Brazil. And then we would see what the delay was between the P and S wave arrivals, and then we would convert that into a distance. And then we would know that the earthquake happened somewhere along a circle that we could draw at the same distance away from Sao Paulo, which is shown in this purple circle here. We would do the same for Paris, France. And if we just did Paris and Sao Paulo, we would know the Paris circle is the orange one. We would know the earthquake either occurred here or occurred here. But once we have a third station, all 3 of these circles are only going to intersect at one particular point, and now we know the epicenter of this earthquake was located in the middle of the Atlantic Ocean here. And this is how earthquakes are located. All these earthquakes that we've previously talked about all over the earth, this is how those earthquakes are located, by looking at information from seismographs around the world and determining where they are.